Boom.
All right, good morning, ladies and gentlemen. Coming to you live a week before winter break. Woohoo! Okay, so starting off today, which table spinning tea went fastest? Which went the slowest, and why?
You remember these things, don't you?
So these are our spinning teas, and we had you do in class. We had you do this one first, and then for the challenge, we had you do this one, which was a little bit shorter lever arm here.
Yeah.
And what did we have? So which one went fastest? Well, this one went faster. This one went slower.
Yeah.
For why? Well, let's talk about the lever arms of this one, right?
Yeah.
So my lever arm here compared to my lever arm here is a lot longer.
Yeah. So it's
right?
going to have a higher
moment of
inertia.
And if we look at our work from class,
Knock them over there.
we can see, so this is the math for this one, which we reviewed yesterday. This one is 0.058 kilograms meters squared, 0.021. And this one is a greater number, higher moment of inertia.
So not only was it larger radius, but there's something hidden in the end here.
We also changed the masses, and in the ends of one, whoa, rogue.
Had steel shot, so there was more mass, not only more radius, but more mass.
In both sides. Might as well say, oh, these ones
Nope,
are-
and then on some of them, like this one, and it should be easy to pull out, they're empty. So not only do you have changes in the radius, but changes in the mass, which resulted in changes of the moment of inertia.
And if you're having trouble thinking about that, go watch the video from yesterday, the day before, where we had that race of the two things going down the track.
Yeah, and
Right.
the hollow one, the ring went slower, and the puck went faster.
Moment of inertia. Okay, what does each variable represent? Well, this represents the stripe on the ground,
Or the string, yeah.
right? The radius. This is the angular displacement, angular velocity, time, angular acceleration, and moment of inertia.
Yep.
Okay.
Challenge.
Units for each of these. So my units for this might be meters or centimeters. Units for radius, again, meters or centimeters. For angular displacement, radians.
Radians.
Angular velocity, radians per second. Time, seconds. Angular acceleration, radians per second squared.
Yeah.
How about for a moment of inertia?
Moment of inertia. Where does that come from? That comes
Should I
from.
pull this up, you think? I'm trying to do it over here.
Yeah, that's torque equals I omega.
Okay, so we want to figure out what this is, and we said torque equals I.
Omega. No. Yeah. Alpha.
Alpha.
Sorry.
Alpha. I like omega. And we wanted to figure out this one, right? So it's going to be like this.
Uh-huh.
So this is a Newton meter, and this is radians per second squared.
What's a Newton?
A Newton is, think about Newton's law, kilogram meters per second squared. And then I'm going to put that meter right there, right? That
Yeah.
needs to stay there. And then I'm going to go ahead and, well, the radians are going to go away, right?
Yes, they do.
Okay, I'm going to flip this, but I'm going to ignore the radians. So it's really just seconds squared, right?
Yep.
Okay, flip that, radians disappear. These are going to cancel. This is like over 1, right?
Yeah.
And we're left with kilograms meters squared.
Kilograms meters squared, the units of moment of inertia.
The moment of inertia is kilograms meters squared. Okay, if you know the angular acceleration for your apparatus, what would be the final angular velocity?
And we got all that stuff. Can you find that in your notes? Do you have that angular acceleration? I think we used the angular version of Vought.
Good.
So
let me
let's
go
use
ahead-
the lab, the one we did.
Yeah, let me go. I'm just gonna write down our information here. V final is what we're trying to find. Our angular acceleration, if I look on my sheet right here, is 0.432 radians per second.
And didn't we have some data about the time it took for the mass to fall?
Yeah, it took us 16.44 seconds.
All right.
4, 4, seconds. Okay.
So what variable is missing?
Okay, well we're missing angular displacement. That means that we use, does it look like this? We're gonna flip-flop these, right? Is that what it looks like?
That's what we did, but what we want to do is we want to solve for omega final.
Oh, for
So
this
you
one.
multiply both sides times acceleration.
Yeah. And then, so we're gonna go, I see. Miss Moore's not solving for the correct variable. Okay, so times omega, these cancel, and then I can add this one, right?
Yeah.
Okay, so acceleration times time plus the initial angular velocity, that's the equation I was looking for. I was like, what does it look like
Hey,
again?
but you know, if you don't know it, you can figure, that's the beautiful thing about this kind of stuff. You can reason your way through it.
We can get rid of this because it's 0, right?
Yeah.
This is 0.432 radians per second squared times 16.44 seconds. And I get, thank you, sir, 0.432 times 16.44, and I get 7.1
Radians per second squared. No, radians per second.
radians per second. Okay.
So we've
Great.
got the final angular velocity.
Okay, I think we need that later. I'm gonna write it up here. Radians per second. Okay. All right. What can we know if we know the spinning T's final angular velocity and moment of inertia? I can erase this, right?
You can erase that. This is kind of a rhetorical question.
Think about it.
It's angular
What
velocity.
are our parallel units for this?
Well, let's just go back and go to the next slide.
Momentum is mass times velocity.
Mass times velocity. That's so simple. That's just one thing times the other.
A 7.5 kilogram bowling ball rolls at 6.4 meters per second. How much momentum does it have?
Miss Moore, this is so simple. This is boring. Why are you making us do
I
this?
know. Well, stick around. Times 6.4 meters per second. This is easy stuff. My confidence is soaring. Times 6.4, and I get 48 kilograms meters per second.
That's so simple.
That's my momentum.
And notice that the units just multiply just like the numbers do.
It's nice. If momentum is mass times velocity, and the symbol for angular momentum is L,
What's going to be the same? Well, I like it over here. What's going to be the same as mass for things going at an angular velocity?
isn't that the moment of inertia?
Yeah.
And my velocity, isn't that omega?
Yes, it is.
Okay. All right, so here we go. Our angular momentum is the moment of inertia equals the moment of inertia times angular velocity. The direction of the L is the same direction as the angular velocity. Right hand rule.
You know, your fingers only. No, we'll get to that in a minute. We're not there yet.
Oh, we're not there. Okay. Do I want to talk about that anymore?
Well, the only thing that I would say is you can only make your fingers curl in one direction without a lot of pain and suffering. So if your fingers curl in the direction of the spin, your thumb is going to point in the direction of the angular moment. I know that it doesn't make any sense, but just go with it.
Roll it. Okay. Use your data to find the final angular momentum of your spinning T.
All we need is the I and the omega.
So we're trying to figure out our final angular momentum here. And our I, don't we have that already? Our I is 0.058. I'm gonna write that right here. That is an 8. And then for our, did we just find that?
We just found that.
All right, let's do this. So 0.058 kilograms meters squared times 48 kilograms meters over seconds. Ooh, okay.
No. We need the final. We need the omega final.
Sorry.
That's a linear momentum.
This one, right?
Yeah.
Sorry, I got too excited.
I was going with you though.
I was like, didn't we just calculate that? It's up there, you guys. Okay, so 7.1 radians per second. There we go. And I'm gonna get my answer. It's gonna be 0.058 times 7.1. And I get 0.412.
0.412.
Okay, let's look at our units here. Kilograms stay.
Meters squared.
Meters squared. Do our radians
over
drop?
seconds squared. The radians go away.
They always go away.
Per second.
Okay.
Kilogram meters.
No, sorry. These are radians per second. So no.
Yeah, no. But you still have the kilogram.
Oh,
with
right
the
there.
meter,
Yeah.
No, you're good. That's just an unusual unit that we haven't seen much of.
Ugly.
But look, you've got kilograms meters per second squared for linear, and you've got kilograms meters squared over seconds. Did I say meters per second squared?
Yeah, kilograms meters over seconds.
And
meters squared over seconds.
so they're related, but they're not the same. It's parallel universes.
Similar, but not the same.
And see how simple that is?
So we found our angular momentum. Now, if I had my average angular
Don't even
velocity-
go there.
Don't
Don't even go there. No.
Okay, I know you were thinking it. Don't even go there. Okay, what is the angular momentum for a 210 kilogram ball rotating on the end of a 1.1 meter string? Think about our thing twirling.
Well, what do we need to find angular momentum? We need I and omega. They give us the omega. Oh, that would be like in the book.
What's that?
Oh, airplane on a guideline. So that's like a mass on the end of a string that's going around a circle. And the moment of an inertia for something that's on the end of a string going in a circle is mr squared. So the I is going to be mr squared.
Meters. You guys see what we did here? So for our moment of inertia for a circle, for a solid, it's mr squared. So
Yeah.
square
That's
that.
for a particle orbiting some distance from the center. So, once again, this is simple stuff.
And you guys have learned this before. Oh, that's not the right number.
No partial differential equations.
Square.
No logarithms.
Thank God. I get 0.254.
So 0.254, what is that? Kilograms meters squared over seconds.
Oh no.
That's just kilogram meters squared. Right. We're just
There we go. Just moment of inertia. Exciting stuff. You guys notice how the units are? It's a lot to deal with, right?
yeah.
It's okay.
So now we plug that into our
Got
equation.
that.
I got ahead of myself.
Bada boom.
For those of you
So-
who don't know, it's Monday morning early.
Kilograms meters squared, and then our angular velocity we said was 10.4
10.4.
radians. Okay, no converting there. We're in radians per second. Okay, times 10.4 radians per second. Okay, we're almost done. We can do this. 0.254 times 10.4, and I get 2.6. We'll call it 2.64.
Yeah.
Okay.
Kilograms meters squared per second. Now you guys are doing this in your notes as we go along, right? That's good student skills. I know you guys are doing this. You're not
You
making
gotta be doing it. Okay, here we go. A 5 kilogram solid disc. With a radius of 0.1 meters spins at that many revolutions per second. What is the angular momentum?
Well, let's see, a solid disk. Let's go to the book here.
What's that? What is your
If you have a solid cylinder or disk, the moment of inertia is 1/2 mr squared, yes? So 1/2 mr squared.
Okay, and then what are we trying to find? What is the angular momentum?
Yeah, so
That's this
that's
one,
going to
right?
be, that's L.
Oh, sorry, momentum. See?
Yeah, but, well, no, you're right, because we got to find the angular velocity first.
kilograms. My radius is 1.
So
Like
we
that,
could
right?
find out the angular. We could just, at the top, mr squared, you could just plug the numbers in up there.
Oh yeah, right here.
Yeah.
So we'll do 1/2 times 5 kilograms times 0.100 meters squared. We'll do that to get our moment of inertia.
I'm going to predict that it's 0.25. I could be wrong. It's Monday. I'm probably wrong.
Times 100 squared, and we get. Oh no.
I forgot to square it.
0.1.
It says 0.0.
I know. And here we go. I get 0.025.
Aha!
Close. 0.0.
The human calculator fails again.
Kilograms, meters squared, because we're talking about moment of inertia. Okay, we'll put that right here. 0.025 kilograms, meters squared. This.
Now the trick is we have how fast it's spinning. It's 0.55 revolutions per second. So we're going to have to do some dimensional analysis here.
Okay, so 1 revolution is how many radians?
2 pi radians.
Seconds is what we want, right?
We want, yeah, and we got seconds on the bottom.
0.55 times 2 in the pi. I get 3.46.
3.46 radians per second.
6 radians per second. So now we're gonna go ahead and multiply that up here times radians per second. I'm loving that you have that thing, Boykin.
I know.
So Boykin has a like extender
A tripod
thing.
here, so I can get way up in the air.
3.46 and bada boom. Okay, so I get 0.087. 0.087
Kilograms meters squared per second.
per second.
And that's the angular momentum.
Okay. So notice what we did here. We use our moment of inertia. We calculate that first. We have to make sure our angular velocity is in radians per second. Oops, sorry.
Oh,
and then
okay.
we're good to go. Okay. Moving on. Assuming the Earth is a uniform solid sphere. Oh, it sounded hollow. It's not hollow. Pretend it's not hollow. With a radius of that much and a mass of that much, what is Earth's angular momentum due to its rotation on its axis?
Well, we need I omega. So the I of a sphere, let's see, solid sphere axis through the center. What is that?
A solid, right?
Yeah.
Just mr squared, right?
That's 2/5 mr
Oh,
squared.
2/5?
2/5 mr squared. And how do they get that? Calculus.
Show me where that's at in the book again, Boykin.
Right here.
Ah, solid sphere. Because the difference is it's not a solid disc, right?
Yeah.
Okay, I'll erase this stuff.
Okay, so now we can find the I. How do we find the omega?
Okay, I'm gonna go to my next slide here, right? Don't you have something about this?
No.
Not yet?
No. We'll get that in a minute.
Oh, bored. Okay, go back. Okay. So, let me go ahead and write these down again.
So what's Earth's angular velocity? We go around. How long does it take us to go around once?
24 hours, right?
2 pi radians in 24 hours.
Like this, right?
1
One revolution time goes in the bottom.
Well, no. You could do 24 hours times 60 minutes per hour times 60 seconds per minute. And I think I've done this so many times. I think it's 86,400.
It is. This number is this number right here, right? 86,000. Let me get it real quick. Let me make sure it's right. 24 times. Oh, that's not right. I don't divide it by anything like that.
No, it's 1 hour is 60 minutes in an hour, and what you want is 1 minute is 60 seconds.
1 minute like this, right?
Yeah, 60 seconds.
Okay, so 24 times 60 times 60?
86,400.
86,400.
Boom, 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 boom.
There he is.
30 years of teaching experience.
Like
And
this, right? That's it.
That's the useless trivia that I come up with.
Okay, seconds.
All right, so that's the time for 1 revolution. So now we have to take 2 pi divided by that to get the angular velocity. No.
Oh.
2 pi divided by it. It's how many radians per second.
Yeah. Because this is 1 revolution
Yeah.
and not many seconds.
Yeah.
1 revolution is 2 pi, like that.
Yeah.
2 pi divided by 86400. And I get this number, we'll call it 7.3 times 10 to the negative 5th.
7.3 times 10 to the negative 5 radians per second. That's the Earth's angular velocity as it spins on its axis.
Okay. So my radius is this, and my mass is that 5.98 times 10 to the 24th kilograms. And it looks like we can find this, and then we can do this, right?
And plug it in, yeah.
Okay, so my mass, so 5.98 times 10 to the 24
It's a
kilograms.
big number.
Yeah. Times 2/5. 6.37 times 10 to the 6th meters squared. That's gonna give me my I.
Ay.
Now, do you do? I don't actually plug this in often.
I do 2 times 5.98 times 10 to the 24th
Okay.
times 6.3, and then divide by 5.
Okay. So 2 times 5.98 e to the 24th times 6.37
Times 10 to the 6, and don't forget to square it,
to the 6th squared, just like this, people.
and then divide it by 5.
And then I didn't need to do it like that, but anyways, okay. And then I get 9.7 times 10 to the 37.
She's a wizard. That's a large moment of inertia.
9.7 times 10 to the 37. 9.7 times 10 to the 37.
That's
Okay.
because the Earth is hecka big.
Hecka big.
No, it's hella big. Actually, no, it's just hecka big. Jupiter is much larger.
Jupiter's hella big. Okay. And then we just multiply it by this, right?
Yes, ma'am.
7.3 times 10 to the negative 5th radians per second. Yep.
Hopefully you still got that number in your calculator. You just...
I do, but it's so far away. Oh, this number I have, yeah. So we'll go ahead and say answer times 7.3 times 10 to the negative 5th, and I'm gonna get, is that right, 10, 7.3, okay, and I get 7.09 times 10 to the 33rd. So 7.0.
That's a large angular momentum.
33rd, talking about kilograms, meters per squared over seconds.
Sweet.
Woo! Lots of scientific notation. So what is
But the
Earth's...
basic math is really simple.
Yeah, it's very easy.
Yeah.
We just got times 10 to the somethings all the time. So that is our Earth's momentum. Cool. The sun rises in the east and sets in the west. East sets in the west. What is the direction?
First of all, which direction is the Earth spinning?
Oh yeah.
The sun comes up over there, goes across the sky, and sets over there.
The sun's not moving, right?
The sun's just up there, and we're spinning underneath it. So what direction are we spinning?
So we've got to be spinning that way.
That's correct.
Right?
We're headed toward the east. Sun comes up in the east first.
Right, so we're spinning this way, so it seems like the sun is moving that way.
Yeah. So what's the direction? Yeah, like that.
Okay, so what's the direction of our angular momentum? Well, which direction is my thumb?
Up through the North Pole.
That's the North Pole. Boom. Okay. All right.
You know what? We could let the students do this.
I think so. We can make this be like their. Well, let's see. What would Earth's LB do to?
So that would be, the Earth would be like
yeah.
a particle going around the sun. That would just be mr squared. So there's the R. You've got the mass from a previous slide. It looks like 5.98 times 10 to the 24. You do that.
All right, you got it. I'll make a little note
We
of that.
ain't gonna do that.
This was a homework.
We lazy.
You guys got it. Okay, moving on. Change of direction here. Change of speed. Impulse changes momentum.
I remember this.
Okay, so impulse, J, changes momentum. We know that force times the change of time, mass and change of velocity.
I remember bouncing a golf ball off my head.
The koosh.
The
Right.
koosh. I remember being in an accident on October 10th and giving a lesson about it.
And how, okay, so how is this Newton's second law?
Well,
What's Newton's second law? Massive acceleration, right?
yeah. So
How do we make this look like acceleration?
I think it has to do with that delta t over there.
If I divide by delta t on this side and divide by this side, velocity over time is acceleration.
So that's basically just an expression of Newton's second law.
Where's my mouse at? There it is. There it is. Did I go one too far? No.
No,
okay,
that's
okay.
it.
How much momentum does a 1,500 kilogram car go in that many meters per second?
It's mass times velocity. That's going to be mv. 1,500 times 20. 15 times 2 is 30 plus 3 zeros. That's going to be 30,000 kilograms meters per second. So it's got 30,000 kilograms meters per second. We don't even need to do that.
So 30,000. You said 30,000 kilogram meters per second. What impulse is required to stop it then? 30,000.
Negative
30,000 kilogram meters per
second.
second. I'm like, what's the number at 30,000? If it comes to a stop in 4 seconds, what is the average force exerted? Oh no, what did we say? What is the
J
average force?
is
Oh, wrong.
delta P.
Delta P.
M
Well-
delta V.
Yeah, M delta V. What is the average force? Well, but we already have this, right? What'd you
We
say?
got
it
the
was?
mass. Yeah, and put a negative in front of it because
Right.
the momentum is decreasing. That means time can only be positive. That means a force is going to be negative.
So if it stops in, so we'll just divide by our delta T. So our force is going to be this
30
number.
divided by 4. Half of 30 is 15. That's going to be 7,500.
30
No. Yeah, 7,500.
divided by 4. I get 7,500.
Boom, boom, boom!
He's on a roll
The
today, ladies
human
and gentlemen.
calculator does it again.
Kilogram meters. Oh, sorry. No, we're talking about force here. Meters per second per second.
Or
That is a
Newton.
Newton.
That would be a Newton meter. Oh no, Newton. No,
yeah,
no,
yeah,
you're
Newton,
right.
yeah.
Newtons.
Okay, so just to kind of reiterate, so how much momentum does a 15 kilogram car going that fast? That is just mass, mass times velocity. We get that, this is this. I guess I didn't have to cross it out, but it's negative. Sorry, it's positive. What impulse is required to stop it? It'll be the negative of the same number. That is equal to the impulse. If it comes to a stop after 4 seconds, we divide by 4. We get the number, that amount. Oh, sorry, negative.
There you go.
Negative that much.
So you guys have done this before. It's really simple. I'll bet that there's an analog to angular motion. Oh!
Okay, here we go. A bicycle with a wheel diameter of 0.8 meters travels at 1.5 meters per second. What is the angular speed of the wheel?
We got the linear. That's meters per second. We need to change that to angular. What's that Rosetta Stone?
So diameter equals 0.80 meters. Rosetta Stone is this.
Yeah.
And how fast they're traveling? The velocity is
1.5 meters per second. That means every second it's going 1.5 meters. It's leaving a 1.5 meter stripe on the ground.
and what is the angular speed of the wheel?
Well,
Like this,
if we
right?
got the diameter, I think we need the radius, don't we?
Yeah, so we'll just divide this by 2. Like that, right? So this is the
0.4 meters.
sorry. Okay. All right. So are you guys? I'm gonna go ahead and just go like this over t, and this is, if I divide this by r, is s over r over t like this.
That's a good way to do it. I like doing it like that.
Yeah, and our stripe is our, so this is our stripe and this is our time. So 1.5 in 1 second. So 1.5 meters per 1 second. And our radius is 0.4 meters.
You guys remember doing this, right?
Yeah, I hope so.
You better.
Okay, 1.5 divided by 0.4, and I get that. So 3.75. And the one we don't even need to do anything.
So the angular velocity is
3.75 radians per second.
simple.
Okay. If we think of the wheel as a 2 kilogram thin ring, like that, what is the angular momentum?
I think we need the book here
We do.
for a thin ring or a hollow cylinder or hoop. That's mr squared. I is equal to mr squared.
Okay, so our I, I'll do it right down here. I is equal to mr squared.
Yep.
And our mass is 2 kilograms.
Yep.
Okay. And our radius is still going to be 4.4.
Yes, it is.
Okay, 0.4 squared.
4 times 4 is 16.
2 times 0.4 squared, and I get 0.32. 0.32 kilograms meters squared.
That's the moment of inertia.
Okay.
Now we gotta find the angular momentum. And the angular velocity is 3.75 radians per second.
Okay, 3.75 radians per second. Let's do this. So just times 3.75.
Yeah.
And I get 1.2. 1.2. And we're talking about momentum. We've got kilograms, meters squared
per second.
Radians disappear. Oh, okay, that is our angular momentum. 1.2.
Yep.
Blah, 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 blah. All right. Look at this. Oh, so just like in the kinematics world, for momentum, we also have analogous characters here. So force and net torque, time, these mass and moment of inertia, velocity, change in velocity, and change in angular velocity.
So just like you were able to do impulse problems, you can do impulse problems that change angular momentum.
Lucky you.
Lucky us.
Okay. All right, so here we go.
So for this same bike, don't erase anything.
Okay. If you put the brakes on, oh, thank you, I almost forgot. If you put the brakes on and roll to a stop in
1.3 seconds.
Okay, so we're braking, we're slowing down. What torque do the brakes apply?
We're gonna have to go to that last slide
Yeah.
because I don't remember. Can we go back to the last slide?
Yeah.
So we want to find the torque.
Okay.
Oh, what do we have? We've
Well-
got,
So wait. So we want to find the torque, but don't we already have this? Did we figure this out
yeah,
yet?
we've got the change of angular momentum. Well, we have the original angular momentum. The original angular momentum is 1.2.
Okay, so let me
If
go
it
ahead.
comes to a stop, that final angular momentum is going to be 0.
So this is gonna be like this, right? Is that what you're saying?
Yes, ma'am.
Okay, and we know that the final was 0
Yeah.
if it's coming to a stop. I'm running out of space here. Equals, what was my inertia? My moment of inertia was 0.32 kilograms meters squared. My final one was 0.
Your original
radians
is 3.75.
minus 3.75 radians per second. Okay, people, plug this into your calculator. I get 0.32. Wait, just 0.32, right?
Yep.
Yes. 0.32 times, I'm gonna say 0, or just, negative 3.75. I get negative 1.2.
Yeah.
Negative 1.2 Newton meters. Okay, so that is,
So what did we just do?
so if you put the brakes on and roll to a stop in 1.3 seconds, what torque do the brakes apply? So we said net torque equals all of these things,
Yeah.
and we already have the moment of inertia calculated. We know it's coming to a stop, and so it's really important that you don't just put 3.75 in here.
Yeah.
It needs to be a negative 3.75 because of the change that's happening. It's coming to a stop.
That's right.
We're applying it forward.
Losing
to
momentum or losing velocity.
Yeah. Okay. What impulse did the falling mass exert on the spinning T? Can I erase this?
You can erase all that. Now, I've disassembled the apparatus, but if you recall, the mass, we measured how much time it took to fall. And let's see, impulse, that's just going to be, what would be the torque? Did we get the torque? So what I'm going to say is,
No, it's right here.
no, it's going to be on this over here.
Oh, yeah, okay.
Did we calculate the torque? Where do we do that?
Yeah, right here.
Okay. So you've got the torque, and that's force applied over a time interval. Do we have the time it took to fall?
We do. 16.44.
Oh, that's simple. So that force, or the torque, over a time interval is equal to the impulse.
Oh, sorry, I'm writing the wrong thing here.
I just put torque times time.
Because this is like,
Force times time.
yeah, this is like force times time.
Yeah.
No, remember impulse.
Yeah.
Okay. And now impulse doesn't have something that directly correlates, but
It
when we're
may,
talking about,
but Mr. Boykin has never seen it before.
we're not gonna talk about it. Okay, so instead of force, we're talking about torque times time. We can figure out the impulse. We just
It's
do
just
point.
0.025.
Okay. We get 0.025 times 16.44, and we get 0.411.
This is a very long lesson, boys and girls, but
It
that's
is.
okay. The homework will be easy.
My units are Newton meter seconds.
Yep.
Is that right? This will cancel out.
Yeah, you got kilograms, meters per second squared times meters.
Okay, yeah. Just kilograms.
So what you get is kilogram meters per second.
This is squared,
No,
right?
yeah, meters squared per
There
second.
we go.
Whew. Have mercy.
Kilogram meters squared per second. Woo, man. Okay. All right, so there it is. The impulse of the falling mass. Okay, a 10 kilogram pulley of radius r is that of 0.5 meters is pulled on with a net force of 50 newtons. What can you know?
Well, let's assume that the pulley is like a solid disc.
Okay.
And if the pulley is like a solid disc,
Solid disk, that means my moment of inertia is
1/2 mr squared.
mr squared. Okay. And what do we say we have?
Good morning, Cougars. Please stand for the pledge to our flag.
Ignore them.
I pledge
Pledge allegiance to the
flag
flag,
of the United States of America,
and to the republic which stands, one nation under God, indivisible, with liberty and justice for those who can afford it.
Okay. All right.
Good
So
morning, Golden Valley. This is for
we can find the moment of inertia.
Welcome to our last
We've got this. What do we say? We have this
last
equals
semester. This is the last
times time, which equals.
Oh, we haven't got that yet. You know, you're way. In fact, let's just go to the next slide because.
What can we know? Starting from rest.
Okay, now what I'm going to say is we're not going to do this. You are.
Starting from rest, the mass drops for 2.5 seconds.
Make it a great day, Cougars.
Okay. What is going to be
I'd like to recognize
the change in momentum?
senior
Oh, sorry, not mass.
He's shown great improvement in academics and maturity. He's doing very well.
Mass times velocity, like that.
Yeah.
Looking forward to
Okay.
seeing him graduate.
Okay, you guys can do this, and I think we're about done, aren't we?
My second person.
Let's go to the next slide.
Amethyst Lumley. There's all-around excellence.
Is that Amethyst Lumley?
Yeah, something! Woohoo!
Situation.
Okay. All right. What is the change in the angular velocity? What is the change in the acceleration?
They can do that.
Yeah. Yeah. How would you do that? Find it. Figure it out. Now you're solving for this at that point, and there's a couple different ways you can find the angular acceleration.
325
Yep.
1854.
Okay. Here is your homework. Other than finishing the problems that we just did, I want you to also read page 239, read page 239 through 241. Good luck.
Boom!